Thank you for the introduction. Yeah, and now for something completely different. Let's move to specters. As you mentioned, I'm Alexey Alexenko, and I will talk about detecting specters in black box CPUs. So this talk, as I said, is about testing CPUs, namely black box CPUs. So we are talking about the situation when the testing target is a CPU that is already produced, so it's a silicon CPU that you would find in an average laptop or a server machine or a PC or something like that. And the goal of our testing would be to find speculative information leaks. So it's the situation when information is leaked through speculative execution. Now, technically speaking, there are already some approaches that can achieve this goal of finding speculative leaks in black box CPUs. So this would be tools like Revisor or ScampV or Transider. But the thing is that those tools, they do not go the full way to finding completely new types of leakage. So they have found they are capable of reproducing known leaks, or they have found some leaks that are kind of like variants of the known leaks. So for example, variants of Spectre 1, but they haven't found so far anything that is like completely new. And for us, the goal would be to try and somehow enable it. So in what I'm presenting today is a few techniques that can significantly improve the performance of such testing, and through the improvement in the performance of testing, significant improvement, we can achieve like deeper testing of the CPUs, and we can do the testing much more holistically, and this way find new leaks. Okay, so let's start with the basics. So what do I mean when I say a speculative leak? So by speculative leak, I mean a situation when a collocated attacker can extract some program's data by observing the microarchitectural traces of this program. And these traces are caused by speculative execution. So the example that we have in here, it contains a leak caused by branch prediction, which could be an instance of Spectre 1. But for us, in this talk, the goal would be to find other CPU optimizations like this. So it's not about branch prediction, it's about finding other performance optimizations that can expose information in the CPUs. Now, how do we approach this problem? A traditional approach to finding these leaks would be to find them manually. So most of the leaks that we know right now, so that would be things like Spectre, Meltdown, Foreshadow, and the others, they have been found by looking at the patterns, at the optimization manuals, by building experiments, doing some experimentation on the CPUs, and this is how they were found. And it's good for the starters to do initial investigation, but in the long term, it doesn't really scale, because this process would have to be repeated for every new CPU model that is released, and it also has a blind spot of it's extremely hard to find leaks that are caused by unknown optimization with this method. Now, an alternative to it would be to use automated tools. As I mentioned, there are a few tools right now that can do such automated testing in a black box scenario. And most of them are based on some form of random testing. So here it's a model that is, it's a representation of model-based leakage testing. Here the idea is to first generate small programs, then so kind of like small sequences of instructions, then execute them on the target CPU and record what kind of information is exposed when we execute this program. So this way we will be capturing, if with many enough of these test cases, we will be capturing all types of leakage that is possible on the CPU. Well, with enough coverage, of course. Then we have a model of the things that we already know about. So this is the model of known leaks, and it allows us to distinguish the things that we already know about and kind of discard them, and only report the instances of the leaks that we have not expected so far. So this is the overall idea of randomized testing of black box CPUs. But this approach on its own, it has its own problem. The problem is that it's a quite inefficient approach because, as you can imagine, it takes a very long time to find something if you are just randomly probing a CPU. So most of these test cases that are generated, they will not expose any useful information to us. So in the tool that I'm presenting today, we changed this approach and introduced two more steps in this process that considerably improve the effectiveness of such random tested on black box CPUs. In a nutshell, it looks like this. So at the first stage, we check whether this randomly generated test case is useful at all, whether it shows any signs of potential leakage on the CPU. And on the second stage, so the useless test cases are discarded, and on the second stage, we take the useful test cases and try to improve them. So this is kind of the idea on the high level. Now, more technically, let's look at the technical details now. The first stage starts with checking whether this randomly generated test case, whether it triggers any leakage at all. Here we have an example with a sequence of instructions which doesn't trigger any speculation, so it will not be useful for revealing anything useful to us. So we can just discard this test case. And we detect it automatically by taking this test case, running it on the target CPU, and monitoring performance counters. If we see that there is no sign of speculation in the performance counters, we can just discard this test case. Now, the second stage after this, we check whether the test case that we produce, whether it contains any speculative leakage. So here we have an example program on the left side. So this is the original program. Here we have a test case that does produce speculation, and there is even some information that is exposed speculatively. But note that this information is already exposed non-speculatively before the branch. So this test case won't be useful for detection as well because it doesn't reveal any additional information speculatively. Now we can detect such scenarios by doing like a tiny small experiment. We can take this test case, execute it on the target CPU, measure the traces, and then modify this test case by adding a speculation barrier after every instruction, which would stop the speculation from happening. Then we take this modified version, execute it on the CPU again, and see whether the traces have changed. So whether we see the same trace or different traces. And if we see no difference, we can discard this test case. Now, finally, after these two filters, we have a test case that shows some signs of potential leakage. Now we want to try and improve it. So here to explain what kind of improvement we make, I need to go a little bit into more background, into more technical details. So here, the test cases that are produced, they constitute of two parts. We have a program and the input to this program. And in order to detect in order to compare the leakage in this test case with the known leaks, we check for non-interference. And to check for that, we need not one input, but actually two inputs that produce the same trace on the leakage model. Now, producing these pairs of model equivalent inputs, it's kind of untrivial, because if you just randomly generate some data, it will produce different traces all the time. So we fix this problem through taint analysis, basically. We take this original randomly generated program and the input, execute it on the model, collect the taints, and then do backwards taint analysis to identify which parts of the inputs they produce the given trace. Then we create more inputs with all the parts of the inputs that are not tainted randomized. And this way we can produce an arbitrary number of inputs with the equivalent model traces. Okay, so these were the three stages, and after all these improvements, only then we are sending this test case that is already checked and that has been improved this way to a complete testing where we collect the leaks and where we compare it to the model. So this is the whole approach. Now let's see how well it behaves in practice, or rather what it gives us in the end. So to evaluate the effectiveness of these techniques, we measured the detection time of different information leaks on Intel CPUs. And here on the y-axis, we have the detection time, note the logarithmic scale, so we have a wide range of the results in here. And first, let's look at at reproducing the known leaks, how much the detection time changes. So here on the left side, on the left bar, the white bar represents completely random testing, and on the right side, we have each of the next bars enables one more optimization. As you see, like the difference is very big. With all the optimizations enabled, we were able to detect all of these leaks within just a few hours. And when we go back to just random testing, so when we disable all these optimizations, it can take hours, or in some cases, the leaks were not detected at all with random testing. So we had a timeout of 24 hours. These leaks were not detected within 24 hours at all. But so far, okay, so we have an improvement in the detection time, but that's kind of a minor thing. The main goal was to find something new. Did we get to this? Yes, we did. So we found two completely new types of leakage on Intel CPUs, on Intel and AMD CPUs. that are based on, well, I will elaborate on this a little bit later, but we were able to detect them relatively quickly within only a few hours. Now, what are these two new leaks? Again, switch. Yeah, okay. The leaks are based, so one of the leaks is based on string operations. So here we found that when you have any string operation, so for example, a string comparison, it can go beyond the bounds of it. So if we are comparing, for example, a 10-byte string and two 10-byte strings, the CPU will actually speculatively go to 20 bytes, 30 bytes, and so on and so forth. So this is the idea with string operations. With divisions, we discovered that there is an instance. So when we have a 64-bit division, so when we are dividing a 128-bit value by a 64-bit value, there is an instance of value prediction on some CPUs, where, well, a very simple type of value prediction where the CPU will predict that the upper bits of the division are 0, just that, regardless of the actual value of the upper bits. Yeah, so this is our findings. I won't be going deeper into the details about these findings. More details are in the paper, but here I want to emphasize that both of these leaks were discovered in the parts of the instruction set that have been already tested before. So they were looked by several researchers in several papers, and these leaks haven't been discovered so far, whereas with our tool we were able to detect them within less than a day, really, of testing. Okay, so these are the results, and finally, let me show you a quick demo. Here we go. I'm not sure if it's legible, but I will try to comment. So here in this demo, we will be testing an Intel CPU. It's an Intel Xeon, relatively recent one, and we will be testing a subset of the ISA. So these will be arithmetic operations, data transfers, and conditional branches. And the only known type of leakage that we know for this CPU within this instruction set is conditional branch misprediction. So we will be searching, is there anything else beyond a conditional branch misprediction? And here we have the demo running with the optimizations on and off. On the left side, I'm not sure if you can see it, but on the left side, the progress goes much quicker than on the right side. The left side is already, yeah, so it actually already detected a leak. And if we look into the test case that was produced, it has a 64-bit division. And this is an instance of the leak that I mentioned before. It's a value prediction on division operations. Whereas on the right side, when we have the baseline, where it's just random testing, it's still testing, and it will be testing on and on and on and on. It will actually take, well, it will take 8.5 hours to detect it. With just random testing. So this is the practical result of the optimizations. So that's it from me. If you're interested in trying it out, it's open source. It's an actively maintained project. We have some documentation. It's on GitHub. And if you want to see the more detailed demo, or if you want a tutorial, I'm here on the conference, so find me, and I'll be happy to discuss it with you. Thank you.
Hey, great work. Just a question about the Spectre snippet you showed.
Yep.
How do you handle like the state of the branch predictors in that case? Is there some way to reset the state, or how was that handled in that framework?
Well, this is one of the more interesting questions when it comes to testing black box CPUs, because you cannot manage the microarchitectural state. And it's not only the branch predictor, it's even more complicated when we are looking for unknown things, because you don't even know what you have to randomize there. So the way how we handle it right now is we have indirect training of the microarchitectural state. So we have these test cases that are executed with the inputs, right? And we execute them like one right after the other. So when we have many enough test cases, the previous test cases will kind of warm up the microarchitectural state for the next ones. So for example, if you have, I don't know, a few inputs that are going in the like true branch, the next executions will mispredict if the input takes the branch on the false branch.
Okay, so this order of the states is basically like also like influencing the results in some case. So it's not like you have the full set that you, there might be a case where test inputs like influence the output of the result, right?
I didn't get it. Could you repeat?
So let's say if you have like a chain that trains the branch predictor always into like one direction, there might be a chance that like you did not find the effect, although there might be one if you train it in the opposite, right?
Well, yeah, of course it's possible, but here the idea is like to kind of simplify it, the idea is that if you execute random code with random data on the CPU, you will get a random microarchitectural state. That's pretty much
So thank you.
what we have, yeah.
Okay. I have another question. If I want to take your framework and try to test it on ARM machines or something like that,
Yeah.
what do you think will be the amount of effort needed in order to translate it to either ISAs?
This is a very good question. Well, the amount of effort, it depends on how exotic the ISA is, basically. Like the closer the ISA is to x86, the less effort you will need to put into, because like in general, like it's possible. It's very, it should be straightforward to port it to other ISAs because we intentionally build the framework in such a way that it should be extensible to other ISAs, to other CPU models, and so on and so forth. Specifically for ARM, we already have a prototype of a port, so we have like early support. We can do some very basic testing, and we can detect like Spectre 1 on Raspberry Pi or something like that. We have it already. If you want to port it to other ISAs, I don't know, RISC-V, for example, something like that, I would say the amount of effort, like for somebody who knows the code base, I would say like a couple of weeks probably, something like that. Yeah.
Thank you. Okay, so let's thank the speaker again.
Yeah.